we will continue section 5 now with objective 3, which is to solve equations containing rational exponents. Remember, rational exponents are just exponents with fractions. And so we can write a radical equation, in fact the ones that we just did, with a rational exponent or fractional exponent. For instance, the square root of x minus 3 minus 4 equals x can be written as the quantity x minus 3 to the 1/2 minus 4 equals x. Because you remember that the square root is really the same thing as x to the 1 divided by 2. I have this defined on the next slide. X to the 1 divided by n is equivalent to the nth root of x, and x to the m divided by n is equivalent to the nth root of x to the m. So rational exponents are really radicals in disguise. The steps that we use to solve radical equations are going to be very similar to the ones that we use to solve these types of equations. Another property of exponents that we need to use is the power of a power property. Do you remember, if you have something of the form like x to the a to the b, that is an exponential expression raised to another exponent, you multiply those exponents. For instance, x to the 3 raised to the 4 is x to the 3 times 4, x to the 12. Well, when we have fractions in exponents, it's not as straightforward as just multiplying and getting the result. I worked out a few details in the textbook where I showed you some specific examples, and those specific examples depend on whether or not the base is positive or negative, and whether or not this value of m is even or odd. Depending on that, it's not just straightforward you get x because the exponents are reciprocals and they multiply to be 1. That is the case when m is odd, but when m is even, you actually get the absolute value of x, and that's just to ensure that your answer is always positive. And so to eliminate thinking about, well, do I need to put x or do I need to put absolute value of x, what we're going to do is just raise each side to the exponent that is equal to the denominator of that rational exponent. Because in that case, we can multiply the exponents and just are always left with x to the m. And I know that probably didn't make any sense, but if you want to trust me, that's fine. If you want to look at those examples that are explicitly stated in the text, please do that so you can get some more clarification. But here are the steps. Just like we did with radical equations, we need to isolate the expression with a rational exponent. Then, like we did with radical equations, we had to raise each side to some number that would remove the radical. So here we're going to raise each side to the exponent that's equal to the denominator of that fractional exponent, because guess what? That denominator, this is really x to the m divided by n. Well, the denominator is really our root of the radical, so just like it was with the radical equations. Then we're going to solve the resulting equation, and again, we have to check our solutions. So here's an example. We have x to the 3/2 is equal to 8. So the thing that we need to do here is raise each side to an exponent that's equal to the denominator. Our denominator is 2, so we're going to square each side. 3/2 times 2 is just 3. 8 squared is 64. So to solve for x, we're just going to take the cube root of each side to get that x is a cube root of 64, or 4. Does 4 check? So we need to ask, does 4 to the 3/2 equal 8? And 4 to the 3/2 means to take the square root of 4 and cube it. And that's really 2 cubed, which is indeed 8. The equation x plus 2 to the 1/3 equals -5. The expression with the rational exponent is isolated. We're going to raise each side to the denominator of that rational exponent, which is 3. So 1/3 times 3 is just 1, so we get x plus 2 on the left is equal to -5 cubed is -125, right? -5 times -5 times -5. We can subtract 2 from each side to get x as -127. And when we check, we get -127 plus 2 to the 1/3. Well, that is really the cube root of -125, which is indeed -5. Here we have 5 times x minus 2 to the 2/5 equals 80. This one we need to do some work to isolate this expression with a rational exponent. We can do that by dividing each side by 5. And so we get x minus 2 to the 2/5 is equal to, what is that? 80 divided by 5, 16. And now we will raise each side to the exponent equal to the denominator, which is 5. So we get x minus 2 quantity squared is equal to 16 to the 5. Now when we solve for x, I'm not going to simplify that right now. When we solve for x, we can apply the square root property to show that x minus 2 is equal to plus or minus the square root of 16 to the 5. So x is equal to 2 plus or minus the square root of 16 to the 5. But the square root of 16 to the 5 is really the square root of 16 all raised to the 5, which is 4 to the 5. And that's a little bit more manageable on the calculator. 4 to the 5 is 1024. And so therefore we get 2 plus 1024, or 2 minus 1024, which is 1026, or -1022. And we can plug both of those in to see that that works. I would note that when you plug in the -1022 minus 2 to the 2/5, note that you would get a 5 times -1024 to the 2/5 equals 80. And so this is to do the 5th root of -1024 squared. But the 5th root is going to be some negative number, but when I square it, it will be positive. In fact, what is it? 4. So we would really get -4. -4 squared would be 5 times 16, which is 80. So the solution set is -1022 and 1026. And keep in mind, there are more examples of these problems worked in the textbook. If you need more practice and solved out problems, please look there. The last of our equation types are solving equations that are quadratic in form. An equation that's quadratic in form is not one that is initially a quadratic equation, but we can make a replacement or a substitution, and we call it a U substitution, and put the equation in a form that is then a quadratic equation. And so that is, we call something U, and when we make the substitution, we get a quadratic equation. So here are some examples. this x minus 3 squared plus 7 times x minus 3 plus 10 equals 0. Notice that we have this base of x minus 3 repeating, and so if we let u be x minus 3 and make that replacement, we just get u squared plus 7u plus 10 equals 0. And notice that these equations are going to be much easier to solve than the original. X to the 4th plus 8x squared plus 12 equals 0. It's not quadratic because of the power of 4, but notice that x to the 4 is really x squared squared, 8x squared plus 12. So here again is that common x squared. If we let u be x squared and substitute that into the equation, we get u squared plus 8u plus 12, which is a nice quadratic equation. The last one, 2x to the 2/3 minus 7x to the 1/3 minus 15 equals 0. Notice that x to the 2/3 is really x to the 1/3 squared. And so that common x to the 1/3 we can replace with u to get a quadratic equation. So notice here that it is whatever is really on the middle expression, and if the first expression is a square of whatever that variable expression is, then we can write this as an equation quadratic in form. So looking at this example, we have x to the 4 minus 8x squared minus 9 equals 0. I could solve this by factoring initially, but we're going to go through and solve it with this u substitution. I notice that x to the 4 is really x squared squared minus 8x squared minus 9 equals 0. So we're going to let u equal x squared. And in place of x squared, I'm going to put u. So now I have u squared minus 8u minus 9 equals 0. And we're going to solve this by factoring. The factors of u squared are u and u. The factors of 9, whose difference is 8, are 9 and 1. We need a different signs and a negative on the larger. So this tells us that u minus 9 is equal to 0, or u plus 1 is equal to 0. So we get u to be 9 or u to be negative 1. Now keep in mind, this is a polynomial equation of degree 4. I should have 4 solutions. Here I only have 2, and that's because I've solved in terms of u, not in terms of x. So a really common thing, a common mistake I see is students forgetting to go back and solve in terms of x. But we have to now go back and make this replacement in terms of u. U is x squared, so this is really x squared equals 9, or x squared equals negative 1. So applying the square root property, we get x to be plus or minus the square root of 9, which is plus or minus 3. And if x squared equals 1, we get x is equal to plus or minus the square root of negative 1, which is I. So we have the 4 solutions, plus or minus 3, and plus or minus I. Another equation, x to the 2/5 plus 3x to the 1/5 minus 40 equals 0. Notice that 2/5 is the same thing as 1/5 squared. So we're going to let u equal x to the 1/5. So I get u squared plus 3u minus 40 equals 0. Factoring, the factors of 40, whose difference is 3, are 8 and 5, plus on the larger, minus on the smaller. So setting those equal to 0, I get that u is equal to negative 8, or u is equal to 5. But now in place of x, that really is x to the 1/5 equals negative 8, x to the 1/5 equals 5. So to solve for x, I have to raise each side to the power of 5 to get negative 8 to the 5, or 5 to the 5.